Well, hello and welcome to the 28th lecture of this short course called Behavioral Theory of Systems with a View Towards Data Driven Control. And we were in the middle of obtaining the equations for the most powerful unfalsified model, where the given data set is a trajectory. So, we have W0, W1, W2, W3 dot this information we have for our data. This is my data set, and from here, so I am going to call this guy as W in general. So, from this I am trying to find out the equations for the most powerful unfalsified model such that this is true, right. And in that process what we notice is that we can break up this process of finding out the equations by restricting the degree of the equations that we are trying to find out. These degrees of the equations, because the degrees of the equations can be found out like this. So, what we do is we define the Hankel matrix of this data H0 W as W0, W1, W2, W3 ... This has q number of rows and infinitely many columns. We define Hankel matrix 1 H1 W as W0, W1, W2, W3 like before, but then we shift this to the left by one step and continue writing it like this. That is my Hankel matrix of order 1. It has size 2q number of rows and infinitely many columns again. So, I am sure you get the trend. H k W in general is going to look like W0, W1 ... up to Wk, W1, W2 ... up to Wk plus 1 and so on. It has k plus 1 times q number of rows and infinitely many columns. And what we notice there is that if we define by n the set of annihilators for this, all are, let me use xi here, yeah, all are xi polynomial row vectors such that R sigma W is equal to 0. This is the set of annihilators of the data trajectory, yeah. Notice that if, so this n, the way I have defined it, this obviously is a submodule of this module, right. It is a submodule. You can easily verify that this is going to be a submodule closed under addition and multiplication, and all the other properties come automatically inherited from the module property of this R1 cross Q xi, yeah. Nonetheless, because this is a submodule, what you can notice here is that if I look at this submodule, then this submodule, being a submodule of a Noetherian model, is going to be finitely generated. So, I will be able to find out a matrix R xi of certain size, finite of course, P cross Q xi, such that the row span of R xi will be equal to n, right. And this R xi is what we are after, because this is the behavior corresponding to, remember that behavior module duality that we had established in our earlier lectures. that each behavior can be associated uniquely with a module provided you have nice properties of the function space. It turns out that the kind of trajectories that we are looking at, that is, this is our function space, right, r q whole to the power z plus. Yeah, with this there is a, like before with C infinity functions, that there is a one-to-one correspondence between submodules of R1 cross Q xi and behaviors. So therefore, with this module I will be able to associate a behavior, and this behavior will then be given by kernel of this matrix R xi. It turns out that this behavior B is the most powerful unfalsified model corresponding to the data. Right. So we will see that this is indeed the MPUM. Okay. What we are trying to do is, we are at least first trying to find out how to get this R xi matrix from the annihilators, but the point is here that to get the set of annihilators, it appears that as if I have to look at all these Hankel matrices. Let me explain again. So remember, I defined n k as the collection of all R xi, which is in n already, which is already an annihilator of the data, but the degree of R xi, remember what the degree is less than or equal to k. See, this is this R xi is a polynomial row vector, isn't it? So R xi would look something like some polynomial here, some polynomial here, some polynomial here, right, and q of them, right. Now each of these polynomials is in itself a linear combination of things like 1, xi, xi squared, and so on, right. So what I do is, among all of these entries, I look at the coefficients of 1 first, and I collect them together and call it R0, right. So these are all the constants from each of these terms. So this R0 obviously is going to be a vector in size 1 cross q, it is a row vector of size 1 cross q, row vector of real numbers. Likewise, I find out the coefficients of xi from each of these entries. That also will give me another row vector. I call it R1, and I write R1 here, and I multiply it with xi, because it is the coefficient vector of xi. So continuing like this, I can write this thing as, how many should I go for? Let us say I go for some number, let us say L, yeah, xi to the power L. I do not have to go any further, because I assume that beyond this all the coefficients are 0. I can assume that because ultimately it is a polynomial, no. So how far do I have to go how far do I have to go in reality? I just look at all these polynomials P1, P2 and P up to PQ, and I look at their degrees. I have to go only as much as the highest degree of these polynomials. Among these polynomials there will be a highest degree, I will have to go only up to that, that is my L, okay, and that is defined as the degree of R. So degree of R xi as a polynomial vector is defined as this number L, which is nothing but the maximum of the degrees of Pi, where I is going from 1 to q. Yeah, that is the idea, that is how you define the degree. And then when you restrict the degree of these polynomials, you upper bound these degrees, the degrees of the polynomials by this given number k, that gives us this nk, alright. Obviously this nk can then be viewed as a, I am not going to view it as a submodule, because submodule will require us to multiply by polynomials and the degree constraints will be broken in general, yeah. So therefore I will view this as a subset of this particular Z1 cross Q xi. This is the module, right, the row module of size Q. I put a k here to mean that now I am looking at all those polynomial row vectors of size Q whose degrees are less than or equal to k. You can easily verify that this is a vector space, yeah, because this is a vector space. Nk is going to be a subspace. What is the dimension of this vector space? I leave it to you to find out. Find out what is the dimension, very easy to calculate. I will tell you what the dimension is, but you have to verify that this is indeed the dimension. This in fact will turn out to be k plus 1 times q. That is the dimension. Okay. Now, with this identification, you see anything in Nk, suppose I take a typical polynomial in Nk, it is going to look like R0, which is a row vector, constant row vector, R1 another constant row vector times xi, R2 another constant row vector times xi squared plus dot 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 plus Rk xi to the power k, right. Okay. I will identify this guy with this row vector R0, R1, R2 dot 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 up to Rk. You see this is an element of R to the power 1 plus k cross times q, or k plus 1 times q, whatever, it does not matter. See that is why I said that this is the vector space dimension is this much. Yeah. So, this is the way you identify this polynomial row vector as a constant row vector, our standard way of visualizing finite dimensional vector spaces defined over the field R. Okay. This row vector. Now, I will not make a distinction between the two. I will, whenever I say that this n something belongs to Nk, I will automatically assume that this might be of this form or this might be of this form, as it is clear from the context. If it is not clear to you, just think about it, it should be. Okay. Now, what we saw in the last lecture was that such a vector R, let us say, belongs to this Nk if and only if R as this row vector belongs to the left kernel, of the Hankel matrix, the kth Hankel matrix produced from the data. Yeah, think about this. So, this is true if and only if this is true, that means the two sets are in fact identical to each other after this identification that you have done. Why is that so? Well, you see, if R belongs to Nk, that would imply this R sigma W is equal to 0, in fact it is identically 0 for all W. So, this would mean that R0 W0 plus R1 W1 plus dot 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 up to Rk Wk is equal to 0. It will also imply R0 W1 plus R1 W2 plus dot 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 Rk Wk plus 1 will be equal to 0. Yeah, in fact it will continue like this forever. R0 times W2 plus R1 times W3 plus dot 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 up to Rk times Wk plus 2 will also be equal to 0. What we are essentially showing is that this vector R0 R1 dot 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 up to Rk, this row vector is orthogonal to W1 W2 dot 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 up to Wk. This, it is also orthogonal up to this, it is also orthogonal up to orthogonal to this. What is this? This is nothing but the Hankel matrix of order k. Yeah, this is equal to 0. So, every column in this HKW is must be orthogonal to this guy, because we have this, and you just reverse the argument like, you know, if you start from a vector which is in the left kernel of HKW, it is going to be orthogonal to all these guys, which will translate to the fact that that R0 W Wi plus R1 Wi plus 1 plus R2 Wi plus 2 plus dot 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 up to Rk Wi plus k will be equal to 0 for all I in Z plus. What does this mean? This means R0 W plus R1 sigma W plus R2 sigma square W plus dot 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 up to Rk sigma to the power k W is equal to 0, which would then mean that this R0 plus R1 sigma plus dot 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 Rk sigma to the power k W is equal to 0, which means R sigma W is equal to 0, which means R xi belongs to n, but the degree constraint tells me that R xi in fact belongs to nk, because degree of R xi is less than or equal to k. Okay. So, you see the two sets are equal. Why is this beneficial for us? Because it's now nice, it's now easier for me to find out these nks. Yeah, I can now find out these nks by just computing the left kernel of my Hankel matrix that I create out of the given data. The question now remains is that how far do I have to go? Yeah, in order to see, when you write down a module like this is my module, yeah, n, and it has it is given by, I know that it will be turn out to be the row span of some matrix R xi. Yeah. This module contains infinitely many elements, and not just that, these elements have possibly no bound on their degrees, right. If you look at, let us say I look at this very simple xi plus 1, it is a scalar system, let us say I have xi plus 1. So, I say xi plus 1 row span of that is my n. Yeah. Now, in this row span, in this submodule, this is a submodule of R xi. So, in fact, it is what is known as an ideal. What is the largest degree element in this ideal? There is no bound on that, it can be anything. Indeed, yeah, if you want, as I explained in the last lecture as well, just multiply this by xi to the power 1 million, yeah, and then xi plus 1. This has degree 1 million plus 1. This also belongs to n. So, there is no bound on these degrees and these in the elements of the submodule that we are interested to compute. So, if there is no such limit, then how to get this all these nks? In order to get all these nks, I need to compute all these hks for arbitrarily large k. Is that even feasible? Not at all. It is completely preposterous to even think that I can calculate nk for all possible k's. So, then my hope of getting this n by looking at this degree constraint, looking at these the parts of the submodule by constraining by restricting the degree, that idea itself becomes now a little dubious. What to do in that case? It turns out that I do not have to go all the way, yeah, I can stop somewhere in between, and that is good enough. And why is that so? So, for that we introduced in the last lecture a few invariants, so to speak, of related to this Hankel matrix. So, first of them was this I look at this hk w and I find out the rank of this guy. The rank of this guy will be defined as dk, okay, and then I defined rho k to be equal to dk minus dk minus 1. This necessitates that I define what is rho 0 because I do not know what d minus 1 is, and I said that this is by definition d 0. From these two invariants, what we had noticed yesterday, not yesterday, the last lecture, is that d 0 will always be less than or equal to d 1, which will further be less than or equal to d 2, which will further be less than or equal to d 3, and so on. This will continue forever, which is understandable because each time when I am going from hk to hk plus 1, I am adding a few new rows, the shifted version of my earlier rows, right, and those may turn out to be independent from the previous ones. Some independence might be there, but still at least each hk will contain hk minus 1. So, whatever the rank of hk minus 1 was will still continue to be the rank, I mean will at least be the rank of the rank of hk will at least be the rank of hk minus 1 because hk minus 1 is a part of hk. Some new rows will be added which might add to the row add to the rank. Yeah. So, the rank of hk might be bigger than or might be bigger than the rank of hk minus 1, but it will at least be the rank of hk minus 1. Yeah. So, that is why each time the rank will only increase or remain the same. So, that is why it is a non decreasing sequence. On the other hand, if I look at rho, it turns out that these rho zeros will actually be a non increasing sequence. That is kind of surprising, and we explained that in the last lecture. Yeah, that happens because when you are adding these new rows, like for example, suppose you go from row 3 to suppose you go from h3 to h4, row 3 tells us how much was the increment in the rank of h3 from the rank of h2. So, remember when we go from h2 to h3, we add q number of new rows. Yeah. Now, among these new rows there will be some new dependencies, yeah, possibly. So, the increment will be some number not more than q, that is the number row 3. Yeah, the rank the number by which the rank increases from h2 to h3. Yeah, that is my row 3. Now, when I go from h3 to h4, remember that when I do this, so when I go from h3 to h4, h4 is in fact h3, and then new versions of shifted versions of the rows of h3. So, what is this? From h3 to h4, if I go, this is w3. So, w4 I have to start from w4 and w5 and w6 and so on. So, that is my h4. Yeah. Now, notice if there was some relation that was being satisfied by these guys, those relations will continue to be satisfied by these these rows as well. See, each of these is a q block row, right. So, there are q rows. So, those rows will continue to satisfy the same equations which were derived from h3 because it is a shifted version. Yeah. And the way this Hankel matrix is constructed, it follows automatically that if there is some R0, R1, R2 and R3, if this row was there in the left kernel of H3, then 0, R0, R1, R2, R3, this will be in the left kernel of H4. This tells us that those relations which were there in the last few rows, last q rows of H3, starting from those last q rows of H3, those relations will continue to be there for these guys. So, those rows which were dependent on the previous rows in H3, their corresponding rows in H4 will continue to be dependent on its previous guys, yeah, because of this fact, because of this shift property. So, therefore, the reduction that was there from Q, which gave us this row 3, that much reduction will be here from Q4 anyway. So, row 4 will will not be more than row 3, yeah, it can be at most row 3, but there could be still some new third order new fourth order equations which are not of this, not like the shifted versions, some new fourth order equations that will cut down on the dimension of H4 even further. So, therefore, the increment in the dimension of H4 from H3, which is row 4, can only be as much as row 3, but if there are new equations, new fourth order equations, then the dimension will be cut down even further. Okay? So, that is why we have this, we had an elaborate discussion as to why this is so. Okay. Now, why is this interesting for us? Because you see, when I have this row 4 less than or equal to row 3, that means row k plus 1 is always less than or equal to row k. What this tells me, very two very crucial things it tells me. First thing is that, as I said earlier, that because it is a non increasing sequence and it is bounded below from below by 0, there will exist a limit, yeah, rho infinity, yeah, this limit will exist. We call this the saturation point, and the limiting, the existence of the limit implies that there exists a capital K such that rho k plus 1 will turn out to be equal to rho k for all k bigger than or equal to capital K. Okay. Yeah, the significance of that is something that we will see very soon. So, this rho infinity will exist, but at the same time we will also notice the following. You see, I said two consequences, this is one of the crucial consequences. The other crucial consequence is the following. Notice when I am calculating these numbers, what does this number signify? Rho k minus rho k plus 1. I know that rho k plus 1 is smaller than or equal to rho k, right, but when I take this difference, which I will define as gamma k plus 1, would it be nicer for you if I define gamma k? That is also fine. In that case, I just have to do this, yeah. So, when I define this gamma k like this, what does this number signify? Can you tell me? Notice, think about this, logically understand this. When I said that rho 4 is less than or equal to rho 3, when is rho 4 exactly equal to rho 3? Rho 4 is exactly equal to rho 3 if all the fourth order equations of all the fourth degree annihilators that I get from H4 are of this kind, which are shifted versions of things coming from the left kernel of H3. If they are the only fourth order annihilators or fourth degree annihilators, then there is then rho 4 is exactly equal to rho 3. That means, the increment that I see in H4, increment that I see in the rank of H4 is the same as the increment that I would have I had seen in the rank of H3 from H2. Yeah, because I am not getting any new fourth order equations, any new fourth degree annihilators. The moment I get new fourth degree annihilators, this rho 4 will be strictly less than rho 3. So, then the number of independent new kth order equations, the number of new independent kth degree annihilators is given by gamma k. Okay. Now, when we saturate, rho k becomes rho k plus 1. So, that means let k be such that rho k plus 1 is equal to rho k for for all k bigger than or equal to capital K, this would imply gamma k will be equal to 0 for all k bigger than or equal to capital K. Yeah, I think gamma k plus 1, right. Yeah, gamma k plus 1 will turn out to be 0 for all k bigger than or equal to k, right, because this is the relation. So, when you take the difference you get 0, and so that means rho k minus rho k plus 1, which is defined as gamma k plus 1, that will turn out to be 0. So, what does that mean? That means beyond the saturation point, beyond the saturation. So, this capital K is my saturation point, right. Beyond k, the saturation point, beyond k, no new k plus first order equations independent, I should write independent equations are found. No new k plus first order independent equations are found for k bigger than or equal to capital K. Yeah. So, that means I can stop my search, because there are no more equations, no more new equations, new independent equations are to be found. All the equations have been found from before, and the new equations, the new higher order equations are just shifted versions, or shifted versions of my earlier equations, right. That would mean that I can stop my search and find out my kernel representation of the MPUM from there, and the fact that this will also imply that this will be the MPUM. Yeah, this and more consequences of that we will see in the next lecture. We will also understand this through a simple toy example. Yeah, but this in the next next few lectures. Till then, take care of yourselves. Bye.